In Chapter 7, certain patterns of composition or behavior in the solar system are discussed. One pattern is that all the orbital and most of the rotational motion in the solar system is all in the same direction, with only a few exceptions. Taking a grand view of the whole solar system from a vantage point way above the Earth's north pole, that motion is counterclockwise. Except for the Oort cloud comets, all the motion takes place on or very near the ecliptic plane, the plane the Earth is on as it orbits the Sun. Oort cloud comets have elliptical orbits around the Sun that have random orientations and eccentricities. The extent of this Oort cloud may be 100,000 astronomical units or so in diameter. The solar system consists of two major types of planets that have a long list of fundamental differences: terrestrial planets and Jovian planets. According to the nebular theory, the solar system formed from a large cloud of gas and dust. This cloud, perhaps a few tens of light years across, began to gravitationally collapse to form our Sun. Planets would be an extra byproduct of this process. Clouds that form stars must be cold, otherwise the gas and dust tends to thermally diffuse away, like a puff of cigar smoke. Our Sun and solar system may have taken between 30 to 50 million years to form. Any collapsing cloud will have some rotation about some axis. As the cloud collapsed, the rotation speed increased, just like the spinning ice skater pulling in her arms. The gas and dust, being a fluid, flattened out due to centrifugal effects, like the flattening of pizza dough as it is whirled around by expert hands. The Sun and planets all formed in this flat, rotating cloud. Thus, the Sun's rotation and planetary orbits are in the same direction and in the same plane. In the constellation Orion, dusty disks surround young forming stars. Some of these may eventually form planets. How does one build planets from material that has the consistency of cigar smoke? Experiments done in the weightless conditions on the International Space Station may hold a clue. Particles can weakly stick together by electrostatic attraction, much like how socks stick to shirts in a clothes dryer when anti-static sheets aren't used. Once formed, these particles grew by sweeping up material as they moved through space. This was the beginning of the accretion process. The larger they grew, the faster they swept up material. When they got large enough, gravitational attraction became more relevant. At this point, they fed on material both on and around their orbital paths. Each orbiting body has an angular momentum simply due to its motion around the Sun. Two bodies in orbit have angular momentum L1 plus L2. When they join together to form a composite object, the angular momentum must be conserved. However, the composite object will not have that same total angular momentum unless it acquires a rotation that is in the same direction as the direction that it orbits the Sun. If it orbits the Sun counterclockwise, then it will acquire a counterclockwise rotation. Generalizing this, angular momentum conservation caused the planets to naturally rotate in the same direction that they orbit the Sun. Planets were constructed of whatever material was available at the location that they were forming. What material was available depended on what material could become a solid at different distances from the Sun. This graph shows the temperature in the early solar system as a function of distance from the Sun. Too near the Sun, everything is a gas. The term condense, in this context, means that substances are going from gaseous state to solid state. There are no liquids forming here. Starting at about 0.3 AU, it is cool enough for rock and metal to condense and form a solid. Terrestrial planets formed from the rock and metal in this region. The frost line, or snow line, is at a distance of 3.5 AU. From that distance and beyond, ices can also condense out and form solids. So, Past 3.5 AU, there is a lot of new additional material from which to form planets. Jovian planets formed past the frost line. Jovian planets, with their large moons, may have formed like miniature versions of the solar system. Recall that the closer a planet is to the Sun, the faster it moves on its orbit. Jupiter and Saturn grew rather swiftly to very large sizes. They got so large that they begin to gravitationally pull in and retain copious amounts of the surrounding hydrogen and helium. This made them swell to even larger sizes. Today, they consist of about 90% hydrogen and are referred to as gas giants. Uranus and Neptune move more slowly on their orbits and thus grew more slowly. They weren't able to pull in as much of the surrounding hydrogen and helium before the ignition of the Sun blew the loose gas out of the solar system. They consist mostly of ice and about 20% hydrogen. They are referred to as ice giants. Asteroids are the small rocky leftover material that orbits the Sun. Comets are orbiting icy leftovers that form past the frost line. There is more than one theory about the origin of the Oort cloud. One is that the gas giants may have gravitationally hurled many comets out of the plane of the solar system into randomly oriented orbits with random eccentricities. The nebular theory explains the general patterns we observe in the solar system. It also allows for random events to have caused exceptions to those patterns. Random events may give different planetary systems many of their different characteristics. Collisions are one type of random process. With so many small bodies forming in the early solar system, they would have occasionally collided. Collisions may have been the cause for Venus's backward rotation and the fact that the entire Uranian system is tipped over at almost 90 degrees. Gravitational perturbations and capturing is another type of random process. A random gravitational capture of Neptune's large moon Triton may explain why that moon orbits Neptune backwards. One oddity that may be explained by a collision is the fact that Earth has such an unexpectedly large moon. A moon the size of ours would be expected to orbit one of the Jovian planets, not a small terrestrial-type planet. The impact theory says that shortly after the Earth formed, a Mars-sized object impacted the Earth, destroying the impactor and knocking out a large chunk of the Earth's mantle. Some of the debris from the impact fell back down to Earth as the Earth was reforming into shape. Some of the debris escaped into space, but the rest settled into orbit around the Earth. That material accreted to form the Moon. There is uncertainty in the details of this process and in how long this entire process would take. Some models show it completing in 1 million years and some in as little as 100 years.